Okay, so yesterday's flipped lesson, and if you haven't seen it, you're going to want to look at that, talks about how we can draw our Lewis diagrams to explain the bonding of ionic compounds. And I did this example up here. And we've also been talking for the last couple of days on how we can get the names and the formulas for these using the diagrams. But there's an easier way to get the names and the formulas. And you would have done this in grade 10 a little bit. So this is a little bit review. And whenever you have a naming system for something that you're going to systematically name things, like using rules, in this case, chemicals. Biology has a naming system. If you've taken biology and you've learned about, and I don't even know how it works, you can talk about the genus, I think, and the species and all that type of thing. So you can break down the name of an organism based on what kingdom it's in, whether it's a plant or an animal, and all that type of stuff. That's a naming system. Whenever you have a naming system, it's called a nomenclature. It's the naming system. So this is chemical nomenclature. It's the naming system. The system we use is called IUPAC, and that stands for International Union of Pure and Applied Chemists. And that's simply a group of old wise chemists that get together and decide what rules we use in order to name things. So it's their naming system that we're going to use. That same group is the group that determines what we name new elements if they're discovered, right? So they're really just a group of chemists that decide how we name things. We're going to start with names and formulas of ionic compounds, and we're actually going to start with the simplest ones. They're called binary ionic compounds because the compounds we're going to talk about now just have two atoms. They're going to have the metal ion and the non-metal ion, okay? All right. So let's first review and talk about the charge on the ions. Now, we've already discussed how to get the charge. I'm going to show you how we're going to find the charge on the ion for the most stable ion using the group that it's in and also using your periodic table. All right? Now, these pictures up here are for an old periodic table. Are they the same as the one I've got up there? Yes, they're the same as the one I've got up there. But I want you to use your periodic table. So if you have a copy of the periodic table handy, oh, and I did give you all copies, didn't I? Get that periodic table out. And you still need one, and you can just keep that one. Just keep it. So get your periodic table out so that we can look at it. If you don't have it with you because it's been misplaced or something, let me know. I got extras right here. I want you to have a table in front of you so that you can find the numbers that I need you to find. Got a table? Yeah, you need it to. I figured John did. I could tell he was just kind of sitting there waiting for a table to happen. Periodic table. You need a table? You got one? Excellent. Okay. This first note describes two situations that can happen when it comes to an ion. Many of our ions have only one possible charge. The term chemists use to describe an ion that has only one possible charge is univalent. Uni representing one. One valence. One charge. Another word we use in chemistry to describe the charge is the oxidation state. The reason we use the term oxidation state comes from history. When scientists were originally studying these elements, they would burn them in oxygen to see how much oxygen they grabbed up, how much What was their state of oxidation? When we discovered electrons and protons and neutrons, we discovered that the charges are why they could grab up oxygen, the way they behaved in their charges. So that's why we call it an oxidation state. Examples of univalent metals. Sodium +1. We've already seen this when we drew our ions. Group 1 is +1. Group 2 is +2. Group 3 is +3. Okay? There are other univalent metals we need to know. Zinc. Zinc is a very common element. It is in the transition metals, but if we look at the charge on the table, I'm pointing right there to that little 2, just like this one here, we'll see that zinc has a possible charge of 2. What I'd like you to do now with your table is find zinc in the same spot. Okay, find zinc. And take a look at the bottom of the box. You see there where it says +2? That's where you will find the charges on your table. When you need that charge, if I asked you for zinc, and I ask, what's the charge on a zinc? You go to the chart, you look at the bottom of the box, you say +2. I say, perfect. Okay? So that's where you can find your oxidation states or your valences or your charges. Take a look at group 1. Notice on the bottom of the box all the way down, what's it say? +1. Group 2? +2. Jumping across to aluminum, what's it say under aluminum? +3. Are we okay on where to find the charges? Okay. Some of our elements have more than one possible charge. Many of them are the transition metals. We're going to talk about these later on, but I just wanted to point them out. If you take a look at iron, now this actually has a mistake. It's got a 6 on it, but I don't know if the oxidation state is 6 for iron. This one doesn't. Take a look at iron. What are the possible charges for iron? 2 and 3. +2 and +3. It can exist in 2 different forms. Copper, you'll notice it says 1 and 2. Okay? So when I'm asking you to find the charge, that's where you're looking. Another important univalent one, silver. Find silver. It's a transition metal. Does anybody remember what the symbol for silver is? AG. And if you track it down, and Amy, she's not putting up her hands anymore, but that's okay. Thanks for blurting that out. +1. I know, I'm just joking. Everybody kind of seeing where you define that? Excellent. All right. Let us continue on. The first types of elements that we're going to name and get the formulas for are binary compounds. Binary means 2. If you've taken any computers, you might have learned about binary language that has just 0s and 1s. I don't know if you've ever learned about that before. Have you ever learned about binary language? No? Doesn't matter. Bi, 2, binary. Tomorrow, we're going to learn about names that have more than 2 elements in them, but the naming system is always binary in nature. What they mean by binary naming is that you will always have a name for the positive chunk, which is the front piece, and a name for the negative chunk, which is the back piece. Because the metals are the positive ions, they're first, and the nonmetals are the negative ions, they're last. Naming binary ionic compounds that have univalent metals are very easy. All we have to do is name the 2 ions. This first one is made up of a sodium +1 ion, so we call it sodium, because that's what we call the ion. And it's made up of a chloride -1 ion, so it's chloride. For binary ionic compounds, they end in "ide." You've heard that before, I think. All right. What's the name of my second one here? Conrad?
Magnesium oxide.
All right. Magnesium oxide. Excellent. This is interesting. I didn't want to do that naming right now. Let me just do a little cheat ahead here. Didn't think I was doing that. All right. Excellent. I'm going to help you with the next two because this has iron in it, right? Fe. This is iron and nitrogen, which makes it nitride. But I need to put something in the middle. I'm going to need to tell what type of iron it is, because when we look at iron, you'll notice it has two choices. I'll be showing you later on how to do this, but this, in this case, is iron 3 nitride. And I'll explain to you how we do that later on. Au. What is Au? Gold. Very good. Is gold univalent? Does it have only one number? Or is it multivalent? Did you find gold? Track gold down. How many numbers are on the bottom? There's two numbers, 1 and 3. That makes it multivalent. That means I need to express which one it is. And I'm going to show you how to do that later on. What's the last word that goes with this? What is this? Oxide. And for our veterans, what type of gold is this, Mark? Yeah, it's gold 3. And I'll show you guys how to do that later on. So we either have them where there's just one possible charge, where I don't need to state what kind it is, or there's two possible charges and I need to state it. Okay, let's now go and just do the simplest ones. So we're going to do now binary ionic compounds with univalent metals. You can watch the end of the video, but I think you've seen this before.
Yeah.
Yep. So binary ionic compounds with univalent metals. Univalent metal, so there's only one possible charge, which means we don't need that brackets there, and we'll use that later. And then the non-metal anion. The metal is always written first in the formula, and then the non-metal. In the name, the metal's name comes first, because that's the name of the ion as well. And then the non-metal name comes last, and it's got an "ide" ending, because that's the name of the negative ion. We put "ide" on the negative ion.
In the university program, do you ever go over the different charges for like the gases?
No. In this particular course? Oh, in the university level, we can explain those using different types of hybridization. If you go back to your notes and you look at hybridization theory, right? If we've got sp3 hybridized versus sp3d hybridized versus sp3d2 hybridized. Okay, so again, for those of you who have devices, you're going to see here that we just basically have some examples here. don't know how close are we. Are we good? We're good to go? John, you're good to go? Okay. And, don't worry about the arrow. It's not a reaction. It's not a big deal. Let's just come up with the names for these. If you know how to do this, that's awesome. Go ahead and write the names. If you've got a pencil nearby, that's even better. It means you can give it a shot, and if you make a mistake, you can always fix it. So I suggest you, if you think you know how to do this, go ahead and write away in pencil. Here, I have some pencils. Oh, you've got lots of pencils? All right. Just saying. Do you need a pencil? Oh, yeah, you're anti-pencil. Why would you wait? What do you think the end of that's going to be called? So why would you wait? I know. So go ahead. You could do that too. What's the name of this first one? Alexis, what's the name of this one? Yeah. Sodium chloride. How about the next one? Yep. Aluminum oxide. Don't worry about the numbers. I'm going to show you where the numbers come from in a moment. And don't worry about naming the numbers. We don't name those numbers in this naming system. We just name the metal ion and the non-metal ion. Aluminum oxide. That easy. Next. Brand number 1. What do you think? What's that next one going to be? Yeah, that's your brand number 1, see, because you're closer to the front. Magnesium fluoride. Fluoride. I have to say it that way because there's a U in there. And I always spell it wrong if I just say fluoride. Last one. What's the name of that? Ooh, battle here. Conrad, what do you got?
Zinc sulfide.
Zinc sulfide. Naming binary ionic compounds are pretty straightforward. Do we have any questions or concerns on that? Okay. The trick, though, is now going from the name to the formula. And that's a little more trickier. We're going to use something called the crisscross rule. I actually call it the crossover rule. Just different textbooks. Doesn't really make any difference. So let's write down the crossover rule, and then I will apply it. So this crisscross rule or crossover rule is really a numerical, mathematical, it's not really a trick, but it's just a process that allows us to get the chemical formula quick and easy without having to draw the Lewis diagram like we did in yesterday's lesson. Now, I have an example up here on the board for the calcium and the chlorine to form the calcium chloride, and this is a good illustration of why it works. So if we take a look at the building of a calcium chloride, you can see that calcium needs to get rid of 2, and chlorine only needs 1. So calcium needs to get rid of 2, so therefore we need 2 chlorines. And you'll see here that the calcium has the 2 electrons, but therefore we need 2 chlorines. It's as if the 2 on the calcium crosses over to determine that we need 2 chlorines. Chlorine only needs 1, so the 1 needed from this chlorine seems to go over to the fact that we only use 1 calcium. And in the end, to make everybody happy to have full outer shells, even though calcium started with 2 electrons, in the end, we ended up with 2 chlorines or 2 chlorides, okay? The way we can mathematically do this without having to draw it out is to ask the question, what charge does the calcium become? Well, we can use our periodic table for that. Calcium is in group 2, so the charge on the calcium is +2. The chlorine is in group 17. It gains an electron, and it becomes, what charge does the ion become when it gains? Yep, -1. And when we cross over the charges and forget about the signs, we get 2 and 1, but we don't, what did I just do there? We get 2 and 1, but we don't write down the 1s, because we don't write that in chemistry. We just implied calcium chloride. And so we can get to the formula by just looking at the charges and not worrying about the diagrams. That's why it works. So let's do some examples that don't involve a Lewis diagram. Let's just do some examples here. Let's just do zinc chloride. So don't write down the title again. Just put EG. EG. Right? EG. Zinc chloride. And this is where your periodic tables are immensely useful. Yes, the numbers are up here, but I want you to track the information down. You write down the symbols, ZnCl. Track down the charges. What's the charge on a zinc ion? 2, +2, +2. Charge on a chloride ion. Be careful, there'll be many numbers on there, or will it just have the 1 number? Did I get rid of all the numbers? Yeah, there are many numbers. Assume it behaves like it should in group 17. What charge do they become in group 17? -1. Cross over the numbers. Zn1, we don't write it. Cl2. I'm hoping in the future you don't have to write the numbers down. You can just kind of imagine them being there and then cross them over. So there's no need to always write down the crossover, right? You know, very often, like in the movie, okay, let's cross them over. All right, let's draw that. We're not going to do that every time. That'd take forever. We're going to get better at it. We're not going to need to cross that. Let's do another one. Again, don't mind those slides up there. That's just for video people. You use your periodic table. Again, pencil, go ahead. Write down the symbols. If you need to write those charges in the corner, that's great. If you feel you can cross them over in your mind and just write them as crossed over, that's even better. What's the charge on an mg? Yep. So don't write it down up there. Where would you write that thing down? By the S, so just put it across. What's the charge on a sulfide? Sorry? -2. Where am I going to write that? Right beside the magnesium. So now I've got Mg2S2, but what was the last rule? I didn't read through the rules. What's the last rule state? Does it say simplify or divide out and put in the lowest terms? What does it say? Reduce to lowest terms. Common factor of 2, I can divide off of a 2. Mg1S1, that's the formula for magnesium sulfide, because I get rid of the 2's. I divide them away. All right? Okay? All right. Let's do another one. Nitride and nitrogen is a little bit like chlorine. There's all kinds of numbers there. But don't forget that we're going to be adding electrons to get stable. I want you to use that simple ion charge that I taught you to figure out how many electrons to gain. So let's write the symbols down. Charge on a silver. And where am I going to put it? Over here? Do I write a 1? No. Charge on a nitride. Yep. -3. That's what I want you to use. Group 15 is -3. Don't mind all those little numbers on your thing. Where does the 3 go? Right there. That's silver nitride. Cross it over. And divide off if you need. There's no common factor between 3 and 1. We're done. We're in the lowest terms. Now that says question sheet, which means I'm at the end of the video, which is fine, and I'm just going to stop my recording, and I'm going to show you what they mean by